ON18, Winter 18, Paper 42. In this example, we are going to look at nuclear fusion, which is something that is very much more cooler than fission, where you take two smaller particles and combine them together. We're going to calculate what is the energy release per reaction and probably use the mole concept. Let's check it out. So in this one, of course, we're going to start off with definition. So state what is meant by nuclear fusion and nuclear fission. Okay, so when you look at the word fusion or to fuse means to bring together. Okay, I'm just going to write here for you. Fuse is to bring together. So for example, you can say, oh, my darling, I would like to fuse myself to you. There'll be a very nice physics pickup line, fuse. But actually, yeah. So fusion is when you have two light nuclei. Nuclei here is the plural of nucleus, okay? Combine to form a single, more stable nucleus. So remember, the goal of all these nucleus is that it was not stable, or it was less stable and it becomes more stable. So this light nuclei will combine to form a single, more stable nucleus. Okay, keyword here is combine. You can always think about the binding energy graph, the shape of the graph that looks like the back of a hill, like this. So when the nucleus are pretty small, they're going to have to find each other so that they can approach 56, which is your goals. Okay, so they will combine and fuse to approach 56. Okay, what about fission? To fissure here means to break apart. So we are breaking apart nucleus. For example, the most famous one is your uranium-235. Okay, it splits into the daughter nuclei so that it can again approach 56. Okay, so we're going to start off first. We will say this is a single, large or heavy nucleus. Okay, splitting, or you can say divides to form smaller, more stable nuclei. I guess a single, more stable, heavier nucleus for fusion. Okay, so make sure you cover all the key points. For fusion, the first one, fusion, we are talking about the nuclei combining to form light nuclei combine to form heavier nuclei. For fission, this is splitting. So for fission, we are talking about large nucleus splitting to become smaller, more stable nuclei. All right. Now, if you are any kind of student who is familiar with CAIE, right, you will notice that this is 3 marks. And so far, we've only written 2 statements. So I don't know about you, but I am full of insecurities. I want to write more. So what else can be written? Okay, so you can say that both processes releases energy. So you could say releasing energy. Okay, and then you could also mention that this one as well, releasing energy. This is the 3rd mark. All right, 3rd mark. You may think it's unreasonable. I agree, but CAIE is like that one. It doesn't hurt for you to write more. Okay, what are other things that you can write to get your 3rd mark? Any other information that has to do with fusion or fission? Okay, so I will give you a list right now. Okay, so other things that you can write is, for example, fusion is initiated by very high temperature. Fission is initiated by neutron bombardment. Okay, think about the conditions. Okay, the resulting nuclei in fission are of similar sizes. Okay, so for example, your barium and krypton, they're about the same size. Both processes releases energy, which is what I wrote because it's the least word to write. Okay, binding energy per nucleon will increase because the product is more stable. Total binding energy increase because the product is more stable. I'm just gonna put a point here. This is because the product, whether the product is smaller nuclei or the stable heavier nucleus, they will both have total binding energy or binding energy per nucleon increasing. So the product is more stable for both fission and fusion. Okay, but don't write this. Talk about things that you can observe. All right, because this is a conclusion, not an observation. So don't write a conclusion, especially at the definition phase. So if you remember how to define fusion and fission, if it's 3 marks, remember to add on a bit more details lah. Okay, maybe the condition of the reaction, maybe certain properties about the products that you can observe. Okay, and finally, fission involves release of neutrons. This is how you can get your chain reaction in your nuclear bomb or your nuclear reactor. If you haven't watched that lecture video about nuclear fission and how we make bombs and reactors, go watch that video and come back here again. We're now going to move on to part B and look at specifically nuclear fusion, especially the reaction that happens into the sun, inside the sun. So the only known place that we have where we can have large-scale nuclear fusion is the sun. In the pipe dream of a lot of nuclear scientists is to create nuclear fusion inside a nuclear generator, because guys, to get isotopes for hydrogen is very easy. You have water everywhere. But to go and find uranium-235 is very hard, which is why if we can find a way to do nuclear fusion in our nuclear power plant, essentially we have solved the problem of we may run out of energy one fine day in the future. Okay, so we can also solve the problem of global warming, but we need to be able to produce this. Okay, so a nuclear reaction which may in the future be used to generate electrical energy is this. Right now we don't have it because it's not possible to increase the temperature and the pressure to match the sun's temperature in an economical way, such that because we use energy to increase the temperature. If I use a lot of energy to increase the temperature, then I do this reaction to create energy, it feels like a losing process. Okay, so which is why if we can figure out a way to carry out nuclear fusion at a large scale, that'll be a pretty significant achievement. But in this question, we're just going to study the reaction. Here you have your deuterium. D is di, 2 ma. So deuterium is 2 because it's di. Tritium, 3. That's why this is 3. They are both isotopes of the hydrogen atom. Okay, so you will have deuterium and tritium combining to form 4,2 helium. But you notice this X here is not balanced, name the particle X. So I'm going to try to balance the proton and the nucleon number. So the proton number to be balanced, this one will be 0. 1 plus 1 is equal to 2 plus 0. And this will be 1. So 3 plus 2 is 4 plus 1. It is pretty obvious to all of us that X is a neutron. Right? Bonus mark. Data for binding energy per nucleon. For some nuclei is given. Okay, so these numbers are given to us in negative 13 joules. Okay, not mega evolt today. So you have a bunch of data, and you're asked to state the binding energy per nucleon of X. But what was X again? X is neutron, and it is all on its own. Do you need any energy to separate it to infinity? No. It's already alone. Separate what? 0 joule, my favorite number. Okay, I guess you could put 0. 0. Next, calculate the energy change that takes place in this reaction. All right, so we're going to have to now do some calculation based on this chemical reaction. I'm just going to copy over the equation now. You can see the equation. I've rewritten the equation of the reaction here. So to find the energy changes, we need to find the initial and the final energy and subtract. All right. So the final energy here, okay, we have the binding energy per nucleon number. So you find the difference in binding energy. Okay, so let me write this for you. The energy change here is the difference in binding energy between reactant and product. Now, if you didn't take chemistry or you don't take chemistry, reactant is before the reaction. Okay, let me write for you. These are the reactants. Okay, after the reaction, you get product ma. This is the product. Okay, so I want to find the difference in binding energy. Just gonna write down delta E. Okay, so I will use the energy of the product minus the energy of the reactant. Okay, I will write it very explicitly for you this time. Energy of your product is only helium, binding energy. Binding energy. Okay, so binding energy of your product is only helium. I will take 11.3290, but this is binding energy per nucleon. So helium has 4 nucleons times 4. Okay, so if you are aware, this 4 is to correspond with this 4 here. Okay, binding energy per nucleon. I need to find the total binding energy. All right, now we're going to minus the product. Okay, so the product, so it minus the reactant. The reactant here is deuterium and tritium. I'm going to minus these two, starting with 1.7813 for deuterium. Again, deuterium has 2, so multiply by 2. This 2 is to correspond with this 2. Okay? Plus, I'm going to continue this process for tritium. Tritium is 4.5285. 4.5285 multiplied by 3. Okay, so the 3 is from here. Okay, so we're gonna now just press our calculator. I know there's a prefix hiding in the table. I'll just include it in my final form. So 1.7813 times 2 plus 4.5285 times 3. Okay, so I'll get 28.1679. But this is times 10 to the power negative 13 joule. If you're feeling a bit insecure about writing your answers this way, you can always just add a big bracket outside. It's like this. This times 10 to the power of negative 13. Okay, so we have this now. And this is your energy change. At this point, you could write in standard form N2SF times 10 to the power of negative 12 joule. Okay, you may be wondering, where are the marks? 3 marks are this one. Yeah lah, this entire chapter is a very big bonus if you know what to do. But oftentimes, when the students study, this is the last chapter, so they forget. But this is an easy chapter. Don't let it go. So to get marks, the first mark is when you know to subtract your this whole thing is 1 mark. So we will look for the students who know how to multiply by the nucleon number, because this is binding energy per nucleon, and then subtracting between the reactant and the product. Okay, so always take the product minus the reactant, because the binding energy for the product will always be greater than the binding energy of your reactant. We have discussed this in the previous example. This is because the product is more stable. So hence, there's an increase in binding energy after reaction. Right? So you show this working and leading to the final answer. That would be the third mark. And of course, the 0 will have 1 mark. Easy. All right, last part. Use your answer in part 2 to determine the energy release when 2 grams of deuterium reacts with 3 grams of tritium. Okay, I want to remind you that this energy that you have, this is this many joule for one single reaction. So the question here remains, for 2 grams and 3 grams of reactant, respectively, how much reaction will we get? So we need to bring in the mole concept. Okay, so I'm just going to bring over the equation here. I'm not going to copy it again. Okay, so we're going to just focus on the reactant now. Deuterium, we have 2 grams. Okay, tritium, we have 3 grams. So this is pretty straightforward, especially those of you who do chemistry. There's no limiting factor. Okay, we have just nice. How do we know we have just nice? Well, we can calculate. Okay, so I'll calculate them one by one. First, I will find the number of moles in 2 grams of deuterium. So this molar mass is also 2 grams. How do I know? Because in chemistry, whenever we see this proton number, unless you are given more information with more significant figure, this 2 grams is your molar mass. So hence, the number of moles in 2 grams of deuterium is 1 mole. Okay, repeat again. Number of moles in 3 grams of 3,1 tritium. So once again, you see this 3 here? This 3 means there's also 3 grams here, molar mass. Mass of 1 mole. So this one also 1 mole, so cute one. Okay, so you can then say hence the number of reaction taking place. For a single reaction, we need 1 tritium and 1 deuterium. So if we have 1 mole of tritium and 1 mole of deuterium, 1 mole respectively, you will get 1 mole worth of reaction, which is 6.02 times 10 to the power of 23. And because of this, hence, the energy release, this is equal to 1 mole, which is Avogadro number. So your energy release will simply be 6.02 times 10 to the power 23 multiplied by energy release of 1 reaction, 2.82 times 10 to the power of -12. Okay, so we're going to put that into the calculator. And this would give us 1.697, I guess 1.70 when rounded to 3 SF, times 10 to the power of 12 joule. You guys, this is a lot of energy, you know. With 2 grams and 3 grams, which is pretty little, you can generate this much energy, which is why nuclear fission and fusion carries a lot of potential in our future to solve our energy crisis. If the scientists can manage to brain this, maybe one day you will help us brain this. How do we recreate this in the larger scale instead of just having it in the lab? All right, so here what we did was, this is for those who don't do chemistry. Okay, whenever you are given a reaction, there are a few things that could limit the number of reactions. For example, maybe I have 2 grams of 2 grams of deuterium and 2 grams of tritium. Meaning I will be limited because this tritium is not 1 mole, it's less than 1 mole. Mole is number of particles. So right now we have the exact right ratio to generate 1 mole worth of reaction. Okay, there's no limiting factor. Energy released by a single reaction is calculated by finding the difference in binding energy. So I just take this one, multiply by the number of moles. So if I give you a different mass, you should be able to calculate how much energy is released based on number 1, how many moles of reactants there are, and number 2, is the ratio enough, or if one is 1 more than the other one. Okay, so that is this part of the equation. And if you're struggling with chemistry, make sure you top up your understanding of the mole concept. All right, so that's what we did today. I hope you learned something, and I wish you all the best in your A2. Go watch a few more videos to top up your understanding and your experience point. Take care, and I'll see you in the next one. Bye-bye.